Great. So we're going to go ahead and get started with the next session. So software-defined networking is really changing the way we design applications. But a key to its success is having good software abstractions and software tools that will allow people to create, test, and compose new and innovative applications. And so in this session, we're going to get a preview of some things going on in the research community toward creating better, higher-level abstractions for programming software-defined networks. And so I'm going to actually give the first talk. So my background, I'm a professor at Princeton, and I worked at AT&T for 10 years before joining the faculty at Princeton 7 years ago. When I was at AT&T, I worked a lot on logically centralized control of backbone networks. And in the time that I've been at Princeton, I've been working a lot on software-defined networking as well. And so here I'm going to give a talk on some work I'm doing with colleagues of mine at Princeton on broadening the view of software-defined networking to include the services that connect to the network. So SDN, and in particular OpenFlow, is letting us program networks in new ways. But in many settings, these networks are just one part of a larger platform that is offering services to end users. And so in this SERVAL project, we're looking at how to include both the network and the services that go over them in a single framework. So if you look at the way the internet was designed 40 years ago, the main abstraction that it was trying to provide was the ability to connect hosts with resources that were located on remote hosts. And so identification of the things you were trying to communicate with was done by IP addresses, the addresses of the interfaces on those hosts. And that enabled a lot of applications like FTP and Telnet that are based on that abstraction. And so as a result, we have a socket abstraction that focuses on communication between a pair of fixed IP addresses assumed to be at a fixed location. And that's a bit of a mismatch with what we have today, which are an internet that's increasingly a platform for offering distributed services to users all over the world. And those users are largely agnostic to what computer is offering them those services and where that computer is actually located. And so that's why we have a bit of a mismatch today with the abstraction of fixed IP addresses communicating and a service platform where now we have replicated services running in multiple locations, changing over time, communicating with users that are increasingly mobile and increasingly on devices that have more than one interface, like a 3G or a Wi-Fi interface on them. And so this introduces a lot of challenges in dealing with multiplicity of servers, multiplicity of interfaces on end-host computers, as well as dynamism, changes caused by things like virtual machine migration and users moving. And so just to look at a few of those challenges, first of all, if you take a service that runs today like a large user-facing web service, you have multiple server replicas at multiple locations. And just keeping track of which servers are up at this time offering this service puts a lot of pressure on updating the domain name system for wide area service resolution, as well as updating load balancers within the data center that have to be updated whenever a new instance of a service is spun up and whenever a service instance fails, leading to lots of different management challenges. Another example of this is virtual machine migration. So it's increasingly used to be able to do load balancing and to move services closer to the users that are accessing them. But because a virtual machine needs to keep its IP address to be able to keep communication alive, it ends up being restricted to working within a single layer 2 subnet, or require complex techniques like triangle routing to be able to direct traffic to a service instance that's moved. So and yet another example of something where the notion of fixed IP addresses communicating is no longer a really attractive service abstraction. And a final example, if you look at mobile end hosts that increasingly connect to the internet over Wi-Fi and 3G or 4G or even Bluetooth, today they can't use those interfaces at the same time for the same connection. And to switch from one to the other or from one location to another, they have to actually break a connection and have applications start them over again. So again, yet another example where the notion of two services or two endpoints communicating is made much more complicated because those services are changing and are forced to break their connections whenever they change. And so that's essentially the issue we're trying to look at in the SERVAL project, is what are the abstractions that would allow us to better support services where mobile multi-home devices are speaking with replicated services that go up or down. And what we need for that are a bunch of abstractions. We need abstractions for being able to define things like what is the name of a service and the kinds of events that happen in the lifetime of a service, like a service instance moving to a new location or a service instance failing. And finally, we need APIs to allow those things to be controlled, not in the sort of manual ad hoc ways they are today, but in much more programmatic ways, similar to the kind of change that OpenFlow has brought to the way we run networks. A second thing we need, and again, it's very similar in spirit to what's happened in SDN so far, is a better separation between the control and data plane, between service resolution policy and service resolution mechanism to be able to make much more flexible ways of controlling those services. So I'm going to tell you a little bit about the two main abstractions in SERVAL, and then I'm going to walk you through some of the mechanisms underneath it, and then tie back together how this relates to software-defined networking. So the first thing we need is an abstraction of a service. And for us, a service is a group of possibly changing processes offering the same functionality. And we need a notion at the network level of a flow of traffic that may be one of several such flows involved in a connection between two endpoints. And that needs to be able to be dynamic so that a flow can change over time during the lifetime of a single connection. So what we have today to identify services are very clumsy notions like IP addresses and TCP and UDP port numbers. And what that means is we have a lot of difficulty dealing with caching of that information by applications and by local DNS resolvers. We have problems where load balancers have to maintain a lot of state to make sure that traffic from the same user continues to go to the same instance of a service when multiple instances share a single address. And these are all very complicated things that we could avoid if we had a service abstraction that had a service name that was decoupled from the current location or instance of that service. So the first thing we're going to have is a service name that is decoupled from the current set of processes that are offering that service, and also decoupled from their current addresses and their current location. And the second thing we're going to have is a flow abstraction, where today we're bound to this IP5 tuple of IP addresses, port numbers, and protocol, which is exactly why it's difficult to support multiple flows in the same connection, and why it's difficult to change the location of either endpoint of a connection. And that's exactly why connections have to break whenever an address changes, and why people go through all sorts of bending over backwards to give the illusion that the IP address is not changing, so that connections can continue to survive. And so what we want to have flow naming that's decoupled from the current IP addresses that those flows are going over. And so I'm going to just walk you through sort of top down how we do this. In SERVAL, essentially what we're doing is revisiting the end-host network stack. In fact, what we're saying is that IP is not the problem, it's the socket layer and the way the socket layer interacts with the underlying network. So today we have conflated identifiers at the application, transport, and network layer, all relying on IP addresses and on port numbers. And what we do in SERVAL is essentially introduce a new layer above the network layer, operating on an unmodified network layer, that is going to just send IP packets. Flows are going to be identified by separate identifiers, as are the services that are using those flows. And as a result, applications can directly bind on service names rather than on ephemeral identifiers like IP addresses or on port numbers. So how does this work? Well, at the top level, what we have is the notion of what we call an active socket. And what that does is applications will now bind to service level names. We call it a service ID. And that service ID could correspond to a lot of different things. It could correspond to an entire distributed web service. It could correspond instead to a particular partition of a replicated storage service like memcached, or even to something fairly fine-grained like a single file or even a single chunk of a file that is being distributed by a group of peers in a peer-to-peer system. So the notion of what a service ID represents is sort of left to the party that's implementing that service. The second thing is to make sure that they're globally unique. They're allocated in blocks, just as we allocate IP addresses or MAC addresses in blocks today. And allocating them in blocks also means that we can take advantage of hierarchy to be able to do service resolution that scales better than traditional flat identifiers do. And finally, unlike today, these identifiers are carried in packets. And in particular, the first packet of a new request to a service includes the service identifier to allow service level routing inside the network and late binding of which instance of a service will handle a particular request. This is going to make things much more scalable by hiding a lot of the churn in which service instances are up or down. And it's going to allow the parties close to the service instances to make load balancing decisions directly on that information, rather than having to dig deeper into the packet to find information that would inform which instance of a service should handle that request. So at a high level then, what happens is that the applications are now written, instead of binding on IP addresses or connecting to IP addresses, will connect instead to service names. And that puts the pressure on the underlying network stack to resolve those service names and to be able to discover them when a new service instance comes up. And we call this active sockets, because what's going to happen now is when a user or an application does a socket level operation, it's going to trigger events that some sort of controller in the network can handle to decide to update a load balancer or to update DNS or to do a variety of other different operations. Unlike today, where those systems are not directly associated with the socket layer. So essentially, the way we handle that, not unlike what you've seen before in OpenFlow, is a clean separation between the control plane and the data plane. This time between the control of service resolution and discovery from the data plane that actually forwards service requests. So for example, if an application makes a request, for example, let's say a service instance is spun up and it binds to a particular service name like X, what's going to happen is automatically the network stack is going to register that service instance so that requests that come to this host for that service X will automatically get demultiplexed to the service instance running there. And more importantly, is going to trigger to some sort of a controller that may be local to the machine or logically centralized in the entire data center. And that controller now can make a lot of policy decisions about how to register or unregister that service with other parts of the network. And in particular, could do so with control plane protocols that are custom made to a particular data center, or use existing mechanisms like DNS, or use, in fact, an OpenFlow controller. And this allows a lot of fine-grained control without actually requiring the network stack to be involved. So the network stack will multiplex and demultiplex requests for services, but won't be directly involved in the policies that decide how that instance is registered or how it's chosen. The next thing we do is we have a data plane that sits in the network stack or in hardware inside the network that can do lots of different actions on service IDs. So think of this as similar to the OpenFlow API, but more service specific. So what's going to happen here is you might have a bunch of policies based on service IDs or prefixes of service IDs and actions that can take place. So for example, you might have an anycast abstraction that says if I get a request, a SYN packet, if you will, for a particular service name, I can direct it to one of a set of IP addresses currently offering this service. I could have also demultiplexed. If somebody is actually offering this service directly on the local machine, I can demultiplex the request to a particular instance of that service running on that machine. If I don't know what to do, I can defer making a decision, pop up to a control plane protocol that will actually take care of doing service resolution for me. Or if I want to do access control at the service level rather than the IP address level, I might decide to, in fact, drop a request for a particular service entirely without having to have fine-grained access control policies based on dynamically changing IP addresses. So essentially, we can do all these policy decisions directly on the service name and directly on the first packet of a transaction between a client and the server. So just to give a couple of examples, imagine you want to do ad hoc service discovery. You want to be able to have a bunch of machines in a local area network be able to operate without any formal infrastructure for providing service resolution. Well, in that case, this client A might have just a simple default rule that just says any request for any service ID should just be flooded to the local broadcast address. So if it wants to be able to request service X, for example, that's available on these two machines, B and C, it can just send a SYN packet to the broadcast address based on that policy. It'll be received by both of these parties as well as a bunch of others who will ignore it, and these parties can then respond with a SYN acknowledgement that includes their own IP address so that the client can now follow up with either or both of those parties to get the service. The same exact mechanism can work for much more scalable wide area service discovery, and here's an example of that, where essentially I can have service level routers in a subset of the nodes in the network, like gateway nodes, for example, or load balancers, that will make decisions based on the service identifier, just like today's routers do it based on IP addresses. So if a packet comes in with a service identifier in it, that particular box can make a decision to forward based on the same local actions. So the same kind of table that exists in the end host network stack can exist in network devices spread throughout the network, and those can perform late binding and service routing based on that service name. So here's just a simple example. So let's see what would happen if you were to try to build a load balancer using SERVAL. So the way this would work, let's suppose a client A wants to speak with a service X, and that service is replicated on nodes D and E. It might have a policy in its own local network stack that just says, hey, forward requests for service ID X to B. B may be a gateway router or the equivalent of a local DNS server that might be learned using DHCP. So it'll put together a packet directed to destination IP address B, the party that's able to further resolve this request, and it'll send that SYN packet in the network. Now it'll reach B, which also is running a service router above the IP layer, and it has two different ways it could forward such a request to either machine D or machine E. And it can pick one either at random or based on a load balancing policy. And so it will in turn, let's say, pick E and forward that request further now to the IP address of E. When machine on E gets this packet, it'll demultiplex that up to the service instance of that service X that's running on this machine, and in turn send a SYN ACK packet back that includes the IP address of E as well as a local flow identifier. So a key thing to note here is that in the forward direction, we see packet getting forwarded through a slightly indirect path through a load balancer, as would happen today. But notice the return path does not go through the load balancer. And in fact, all subsequent traffic between these two parties goes directly between them without using the load balancer. So unlike today, where you have to have a load balancer in the path for all the traffic between a client and a server, the load balancer is only there to pick a single service instance and then gets out of the way so that the communication can take place directly between the two endpoints. Now, here I've shown an example with just a single flow, but you could imagine wanting to have multiple such flows associated with a single connection between a client and the server. And so there's also a flow table in our architecture that allows a single socket to be associated with multiple flows. And each of these flows can be dynamically associated with IP addresses on the local machine and on the remote machine. So just to show a simple example of that, you could imagine, similar to the example I just showed, that a client might connect an initial flow to a particular server, but over time might decide to add an additional flow that goes between two other interfaces on the two machines. Now the traffic can be split over both of these interfaces, allowing much better performance and reliability. Now let's suppose one of these fails. For example, let's suppose the connection at A3 on the server fails. No problem. The server can essentially signal in-band saying that A3 is no longer available, and in fact, that flow should now start using the IP address of interface 4. And so that would just allow that single flow to fail over to an alternate interface and allow the service to continue. And the same thing happens to handle mobility, virtual machine migration, basically in-band signaling to change the local endpoint identifier of a particular flow without having to worry that the other endpoint has to change how it identifies itself. And so this allows us to offer all sorts of different notions of mobility, migration, and failover using a single, very simple mechanism. So our prototype system is implemented as a Linux kernel module, and we essentially make some small modifications to the BSD socket API to add an address family that operates on service IDs. Otherwise, the socket abstraction looks much the same as it does today. You're just binding and connecting on service names rather than on IP addresses. To be able to handle legacy middle boxes, we essentially can encapsulate our packets in, say, a UDP packet or TCP packet to allow them to get through legacy middle boxes. And we've also developed a translator or a proxy that will allow a SERVAL machine to communicate with legacy machines that don't speak it. This would allow, for example, mobile devices to take advantage of multi-homing and failover while speaking with services that don't yet support SERVAL, and vice versa. Someone who has a front-end proxy in front of their replicated web service could speak SERVAL between those two components without the end user having to have a device that speaks SERVAL. So we've done a bunch of performance tests. We basically get the same performance as the existing TCP stack in Linux. And we've implemented a bunch of applications by just making minor modifications to how these apps call the socket layer. And so just to give you an example, the Firefox browser, we just changed around 70 lines of code, particularly where socket calls are made, to replace things like the get host by name call and the socket binding and connecting to use service names rather than addresses. So relatively modest changes to applications. We've implemented a bunch of example applications, like a replicated web server that supports failover and load balancing. We have a key value store where we can directly route to memcached backend storage systems using the request ID, service ID to correspond to the key in the memcached instance. And finally, support for mobile devices and for virtual machine migration to be able to allow endpoints to change their addresses over time to support failover, VM migration, and user mobility. So just stepping back now, how does this all relate to SDN? Well, the key thing here, and it's very much the same idea we've seen in many other designs of SDN, is we have a logically centralized controller that's interacting with a data plane over a standard interface. And so for us, we're including the end hosts in the mix, as well as a controller API that can allow service IDs to be registered and discovered, and for endpoints between two connections to be signaled at the behest of policy that runs on a separate controller, separate from this data plane. So essentially, our data plane is this service table or service information base, and it's very much like the forwarding table in a router, except it's operating on service IDs or service ID prefixes rather than on IP addresses or MAC addresses. And so essentially, our controller now can talk not only to OpenFlow switches, but also to servers that are running service instances based on service IDs. And likewise, our controller can react to events that happen in the network, like service instances going up, going down, or failing, based on local policies, much like an application written on top of OpenFlow can react to packet in events or switches or links going up or down. So in closing, what we've essentially done is moved SDN beyond the confines of the network switches to include the services that run over the network. And in our ongoing work, we're looking at how to exploit our ability to control service resolution and discovery more flexibly, and how to do path selection more flexibly to take advantage of the extra flexibility we're affording. So if you're interested to learn more about SERVAL, we have a webpage at servalarc.org, and the papers, demos, and also the source code are available there under a GPL license. So I'd be happy to take questions.
Hi, it's Eddie Ryan from Cisco. It's a very nice idea. So I have 2 questions. One is you mentioned a service ID will need to be allocated globally. So who will be doing that? And do you see the same problem with the V4 address? The second.
Yeah, that's a great question. So you could imagine if you're doing a local deployment of SERVAL just within your own geo-replicated service, you could imagine just having your own set of service IDs. If you want to do something globally based on SERVAL, you'd need some sort of address hierarchy, just as we allocate MAC addresses through the IEEE or IP addresses through ICANN and ARIN and other registries like it, just to ensure global uniqueness. And we've made the address extremely long because, as you can imagine, the number of services might end up being much larger than the number of hosts. And there's some advantages to being able to have things like self-certifying service identifier. So the low order bits of the address could potentially be a hash of a public key that corresponds to the service.
And the second question is if the middle route fragmented packet, then what do you do with the service ID?
If a legacy middle box or
either way.
So if it's a SERVAL-enabled middle box, that's no problem. It'll index off the service ID and make load balancing or firewalling decisions directly based on policy expressed on the service ID. If it's a legacy middle box, we're forced to tunnel through it using, say, UDP encapsulation. So no free lunch there. If we have to get through a box that doesn't speak SERVAL, we have to encapsulate.
Okay, thanks.
Great, so thanks. Oh, sorry, one more question there?
Well, I guess that's a related question. If you really want to do, contact some service and have a, communication with one of possibly equivalent services, I mean, there's a lot of services that can be considered almost the same for some particular need, but different for related other needs. Or maybe there's also some security considerations. You don't want to use a service that's in a locked office somewhere or something like that. So, I mean, have you thought about, let's just say that this is a successful idea. Well, the very next problem is going to be exactly that. People, they believe it works so that they want to use it and find services. And the service discovery operation is, it's quite complicated. So I'm wondering if you have gone anywhere towards being able to classify and identify services, and especially for any CAS groups.
Yeah, that's a great question. I think the key is the party that's offering the service decides whether they want to give all the instances of a service the same service identifier. And also if they have load balancers that are dictating which instance of a service is picked, they might do that on much more fine-grained kinds of parameters than what I described here. For example, they might do it based on the IP address of the client requesting the service to direct them to a close copy of that service. So there's a certain amount of flexibility within that. And to the extent people really want to view two things that are very similar as semantically different, they could essentially give them separate service IDs. So it's a bit of perhaps a lame answer in that sense, but it's really, the good thing is it's in the eye of the beholder. Whoever wants to offer the service decides the granularity at which they want to decide what a service ID corresponds to.
Thank you.